as Marietta said, I'm Sarah Jones. I've been at NEL for just over a year now, and during which time I've been working on this project, primarily involved with the testing aspects. Other projects I'm currently working on are another EMPIR project on domestic water metering in the real world, and a research project on in situ verification of multiphase flow meters. And I'll start this presentation with an introduction and background to the project. Over half the world's energy needs are met by oil and gas, an increasing proportion of which is being produced as a multiphase fluid. As you can see at the pie chart on the right, the orange and the blue are the petroleum and natural gas aspects. Under field conditions, multiphase flow meters exhibit a high uncertainty, and that can cost industry billions in exposure and also can produce inefficiencies in production. The only way this can be reduced is by innovation and product development. If there are perceived measurement inconsistencies between laboratories, then that can erode the confidence in multiphase flow meters and is also a barrier to product development. So there is a critical need for inter-lab harmonization. So this project is MultiFlowMet 2, Multiphase Flow Reference Metrology 2. It's funded by Euromet through EMPIR, and it follows on from a previous project, MultiFlowMet. And the aim is to establish a reference network of multiphase labs that are consistent and comparable, so that you can take a multiphase flow meter to any of the labs and know that you will get the same results. This will lower the uncertainty of measurement and increase the confidence in the use of multiphase flow meters. Another aspect of this project is to carry out fundamental research to develop various modeling techniques for significantly improving the characterization of multiphase flows. And as part of this, full-scale parametric experiments were performed to directly inform the analysis and testing for the intercomparison process. The project started in June 2017 and ends at the end of this month. And it includes an advisory board of stakeholders, including oil companies and regulatory bodies. And there is a project website, just search for MultiFlowMet. The participants. In the UK, we have TÜV SÜD NEL Limited, who I work for, University of Glasgow, Coventry University, University of Leeds, Cranfield University, Industrial Tomography Systems plc and Petroleum Software Limited. In Germany, we have PTB and Rosen. In the Czech Republic, we have CMI. In the Netherlands, DNVGL. In Finland, VTT. And in Norway, Norse, OneSubsea and Roxar Flow Measurement. There are representatives from the National Measurement Institutes or designated institutes, which are VTT, PTB, CMI, and ourselves. And the labs, multiphase flow labs included are NEL, DNV, Norse, and Cranfield University. Overseeing the test work and the analysis are the independent arbiters, which come from the University of Glasgow and VTT. And the instrumentation developers are ITS, Coventry and Leeds universities from the UK, and Roxar from Norway. The work has been divided into 4 technical work packages. Work package 1 is the preparation for the project, which involves the protocols and test matrices and methods, as well as the logistics for moving the instrumentation between sites. Work package 2 is the intercomparison testing itself to quantify interlab measurement consistencies or variances. Work package 3 is the research and modelling aspects, looking at enhancing the understanding of the character of multiphase flows. And both work package 2 and work package 3 feed into work package 4, the analysis, which combines the intercomparison measurement data with all the flow pattern evidence, the research and the testing from the previous work packages. So to begin with, we'll look at the intercomparison specification, design, and instrumentation build, which is prepare the core instrumentation, finalize the test matrix, and plan the logistics. First of all, we need to design what we call the transfer package, which is the instrumentation package to be transferred between the laboratories for the testing, which comprise the multi-phase flow meter and the flow visualization equipment, and then a logistics plan for shipping between laboratories, which was non-trivial because it involved radioactive sources. Then there's developing documents to ensure the consistency. There's the test protocol as to how the tests were set up and run, and including the roles and responsibilities for all the parties. Test facility uncertainty calculation methodology, which is very important for the analysis later on, and to devise test matrices for each laboratory, and of course data control for the handling and storage access and security aspects. So this is a drawing of the transfer package. The core is the multi-phase flow meter, which is installed as standard with in a vertical orientation downstream of a blind T. That was on a separate skid, and on a different package was a length of pipework which included the ITS tomography equipment, which was electrical capacitance tomography and electrical resistance tomography, the Coventry University Atut East electrical capacitance tomography sensor, and a video viewing section. As well as that, there were, in the blue pressure transducers were set to record at 40 Hertz to provide any additional information, and the green ones were reference pressures and temperatures that were monitored at all the laboratories. For the test matrix development, it required a look at the laboratory operating envelopes. And these are plotted on a graph, as you see, with gas flow on the x-axis and liquid flow on the y-axis, with lines showing the various diagonal lines showing the various gas volume fraction percentages. This is just an example of how it works. So for lab A, there's a range of tests they can do at 10 bar, and then to the right, there are some tests that can only be carried out between 5 and 10 bar, and further to the right, tests that can only be carried out between 2 and 5 bar. And then superimpose on that lab B's capabilities, lab C, and then lab D, and then the common area. There is a common area for all the labs where the testing can always take place. But there's also another area which was also of interest, could also be of interest with the high gas flow rate, which is a common area for 3 labs in this case. Of course, it's important that any testing area can be tested by at least 2 labs. And then from this, the test points are specified, and the number of points will depend on the available timeframes and budgetary limits. For the laboratory fluids, all the labs were testing with nitrogen, and they were all testing with a sodium chloride solution of the same density. But the oil was different for each laboratory. So it's very important to compensate for the different oil characteristics to get comparable test matrices. There was a lot of work done in Multiflow Met 1 on matching dimensionless numbers. And there's never going to be a perfect match between all loops due to difference in oil types and limitations in operating ranges. But the focusing on matching the Froude number is the key aspect. So there's the best match of Froude number via pressure, and matching the oil Reynolds number via temperature, using temperature to modify the viscosity of the oil. And then all the labs were using a set salinity. For the flow pattern determination techniques, there were a number of different ways of doing this. In the transfer package itself, there was equipment from the industrial tomography systems, University of Coventry, and the high-speed video and the pressure recording. The ITS equipment included electrical capacitance tomography at 100 frames per second, which measures gas and oil. The resistance tomography section at 800 frames per second measures the water and oil, or water in the non-conductive phase. And then there's software to combine this data to measure the full spectrum of gas, oil, and water phase fractions across the diameter. The University of Coventry has the ATUT electrical capacitance tomography section recording at 1200 frames per second, which is their research tool is clamped on externally around a perspex viewing section. We've also got high-speed video at 240 frames per second, the pressure recording at 3 locations at 40 Hertz. And additionally, for the Cranfield University tests in Work Package 3, they used a wire mesh sensor as another tomography instrument. So a little more about the tomography and the principle. Basically, sensors are placed around the pipe wall, and selective pairs of sensors are energized, and the field distribution is measured. For electrical capacitance tomography, the sensors are not in contact with the fluid, and with the resistance tomography, clearly the sensors have to be in contact with a conductive fluid. So both ATUT and ITS determine the permittivity in the ECT for the oil and gas distribution, and additionally ITS determine the resistance for the water oil or water gas distribution. They also have to take reference values for the test fluids, and then they use some extremely complicated mathematics to reconstruct the image from the values recorded. And from that, they get the phase concentration for each frame. And by stacking the individual frames, they can see the flow regime with time, as can be seen in the bottom left-hand picture. If you have two sensors at different axial locations, you can use cross-correlation to determine flow rate as well. The ATUT system uses a dual plane system to determine the oil flow velocities, and the University of Leeds has additional software to determine the bubble distribution. Both ITS and ATUT have research solutions and industrial products, and we were using the research versions on these tests. One of the other aspects that we used was high-speed video recording. I'll play the video of this test in real time. I'm afraid it may well be pixelated when it comes across to you because it's a very big file, but you should be able to see the slugging flows. So this is in real time. You can see the slugs, hopefully, you can see the slugs passing through, and then the stratified flow in between the slugs. And then this is the video slowed down and played back. It's the same test, the same video, playing back at 24 frames per second. And hopefully this will not be pixelated. And it gives a much clearer definition of the interface between the phases. The test conditions here were a gas volume fraction of 67% and a water cut of 10%. So onto the intercomparison testing program itself. So this was to quantify the interlab measurement consistencies or variances. So the transfer package was built and commissioned at NEL, and the first round of tests was undertaken at our laboratories as well. It was carried out at 9 and 4.5 bar G and at a controlled temperature of 45 degrees Celsius in order to get the viscosity correct. Once the tests were complete, the transfer package was dismantled and packed and dispatched to Norse in Norway, where tests were carried out at 4.5 bar G and ambient temperature. The rig was broken down again and transferred to DNV in the Netherlands, where they conducted tests at 8 bar G and at a controlled temperature of 18 degrees Celsius. Then the transfer package came back to NEL for repeat tests at the full test matrix at 9 bar G and 4.5 bar G as before, and at 45 degrees Celsius. The test matrices, the high pressure test matrix comprised 97 test points and was looking at a range of flows, as you can see on the right, from high to low gas volume fraction and from high to low liquid flow rate. The low pressure test matrix was 48 test points and didn't cover quite as large a range. But you can notice that some of the higher liquid flow rates are missing from the test range. And that was primarily because the pressure drop through the transfer package. The maximum flow rates achievable were determined during the first round of testing at NEL, and that influenced the matrix set points. And it was anticipated that it might be necessary to remove a number of test points from the test matrix during subsequent test rounds at the other laboratories if the test points were found to be outside their operating capabilities. The intention was to run the test matrix in the same order at each participating facility to avoid the introduction of any additional uncertainties as a result of hysteresis of flow pattern development or transitioning from oil continuous to water continuous conditions. In practice, this was not always feasible due to the different operating principles at the three laboratories. Then on to supporting research and modelling. So this was carried out to enhance the understanding of the character of the multiphase flows and look at how it varied by altering different rig configurations, etc. So there were full-scale tests carried out at NEL to look at the influence of varying the gas injection point. And you can see in the schematic of the test rig here, up in the top right, there's the oil and water mixing assembly, then turns through 180 degrees to come down to the transfer package and then onto the downstream control valves, which set the back pressure in the test rig. So the points looked at were 0D, which was just upstream of the viewing section, 100D, 300D, and 600D. And there were, at each point where feasible, there was injection from the side and injection from from underneath. And some pictures. So flow is left to right. So the side injection is at the 3 o'clock position looking downstream. This is again looking at from a different angle, and injection from beneath in the 6 o'clock position, always through a 90-degree T. For the full-scale test, the test points were selected from the intercomparison test matrix and were repeated at each gas injection point location. And they were selected to give both oil continuous and water continuous tests, and were at 0, 25% and 75% water liquid ratio. And the range of liquid and gas velocities were extended to cover the full range of possible flow patterns. And here's just a sample of some footage looking at the difference in the flow pattern between injection at 0D and at 600D. And the difference is quite noticeable. For the 600D, the flows had a chance to settle down, and some of the droplets suspended in the gas have settled out. And then this is just a video of another test comparing 0 to 100 and 600D visual results. The full-scale tests at DNV were to look at the influence of fluid density ratios. So they replaced the nitrogen in the test rig with argon as being a much heavier gas, and the test pressure was increased to 33 bar to further increase the gas density. So that gave quite a different gas-liquid density ratio, and they carried out a number of tests with those conditions. At Cranfield University, they did some small-scale tests to replicate the full-scale setup. The pipework was all clear PVC. It's not quite as transparent as Perspex, but it does allow the flow pattern to be seen all the way through the test rig, and so throughout the model transfer package. On the right, you can see the horizontal section approaching the model multiphase flow meter. The next picture, second picture from the right, shows where the multiphase flow meter would be. There's a blind T at the bottom, and then in the vertical section is mounted a scaled replica of the Venturi in the multiphase flow meter. There's various different instrumentation in this rig. They were using ECT, electrical capacitance tomography, in the horizontal section, which you can just about see here. They have conductivity rings to measure water levels. They've got a pair of wire mesh sensors. One can be seen at the end of the horizontal section of the transfer package, and there's also one which you can't see near just downstream of the multiphase flow meter. The wire mesh sensor looks like this in the bottom left-hand corner. It's got two sets of wires that are positioned at right angles with a small gap between them. And by energizing different pairs of wires, you can get the phase fraction where the wires cross. So you can actually see what's happening all across the pipe. It is, of course, very invasive and intrusive, and does tend to shred the flow So, but the flow does tend to re-establish quite quickly after the wire mesh sensor, depending on which flow regime you're looking at. And they were also, of course, measuring pressures at various points in the test rig and videoing. As well as the experimental work, there was also numerical modeling work, computational fluid dynamics. And the aim of the modeling was to validate against both the tests at Cranfield and the full-scale tests at NEL, Norse and DNV. And to support the data analysis by being able to show possible reasons for any variances. CFD is a very time-consuming exercise, so a representative selection of model geometries and test cases was chosen. So, to the analysis and conclusions. This is work package 4, and as I mentioned before, it combines the intercomparison testing and the research and modeling from work packages 2 and 3 to verify the consistencies, rationalize variances, and establish a harmonization between the laboratories. For the tomography, a number of tools have been developed to display the results in various different ways. Both of these were developed by the University of Leeds. At the top, there's a bubble visualization tool. Usually, the classic way to display tomography is as a percentage of your phase. So 0% is all liquid and here, and 100% is all gas, and you get a rainbow color in between to dictate the void fraction. The bubble visualization tool displays this in a different way to give a better understanding or a better visual representation of the flow. And here, if you've got a void fraction of 60% or less, then it assumes it's gas, it displays it as gas. And if you've got a liquid content of less than 5%, then it assumes that's fully liquid. And in between, it shows bubble sizes that relate to the percentage of liquid. And you can see on the right-hand side at the top, there's a composite video image of the flow. Below that, there's the classic representation of tomography data. And under that, the representation using the bubble visualization tool. Another tool that the University of Leeds has worked on is data fusion. With the two measurement capabilities, the ECT and the ERT. From the ECT, you get the oil and gas concentration. For the ERT, you get the water and non-conductive phase concentration. And the University of Leeds has developed a way of combining these to get the 3-phase value. So at the top here, you've got the ECT. In the middle, you've got the ERT, and at the bottom, you've got the fused phase distribution. And it also can display as a pie chart the phase distribution for a particular time period. And if the flow visualization techniques can be analyzed and compared, we've got a video here of the tests and the CFD. This is some of the tomography results. And here are more, more comparisons of video against modeled results. And the analysis combines all this information so that if there are any variances between the data, by looking at all these different aspects, you can generally find a reason why they don't match as closely as you would expect. The key to successful intercomparison is reproducibility, which is defined as the closeness of agreement between the results of the same measurand carried out under changed conditions of measurement. And there are a number of changed conditions, which may be the principle or the method of measurement, who's doing the measuring, what instrument you're using to measure it, the reference standards for your measurement, where you're doing it, the conditions of use, and time. And one of these ones were minimized by following a test protocol. So everyone was following the same principles and method of measurement in the same way and using the same conditions of use. The reference standard for the laboratories, the effects are minimized by additional single-phase tests at each laboratory, and these were used to double-check the reference meter uncertainties that were quoted. And as for time, the effect of doing the same measurements but at different times was minimized by carrying out repeat testing for NEL in round 1 at the start and round 2 at the end. And then location. This is the objective of this project, is to show whether the effect of location can be quantified and minimized. Then the data from all this, the testing, physical testing, was analyzed. It was undertaken following an international standard for measurement methods and results. The reproducibility uncertainty was calculated. In MultiFlowMet 1, a comparability parameter was defined, and this has also been used in the intercomparison analysis for this project. And there are various other statistical investigations looking at comparing flow meter deviations. The final stages of the analysis are underway, and published reports will follow, and further details will be in the workshops, which I'll talk about shortly. So in conclusion, the multiphase transfer package was successfully designed, built, tested, and deployed at the 3 laboratories. The test protocol and the method of matching the conditions was found to be successful. The data comparison methodology has combined facility and multiphase flow meter uncertainties in a way that permits the facilities to be compared against one another without explicit reference to the performance of a multiphase flow meter. A successful intercomparison was performed across a wide range of parameters: oil, water, liquid, gas. There were some unresolved anomalies identified in a minority of cases. There were some variances between the laboratories for some single-phase flow conditions that could not be, the reason for which could not be proven conclusively, but some possible causes have been identified. And in a small minority of the data in the gas comparisons, again, variances were observed, and possible causes have been identified as line pressure and sensitivity to flow pattern. One of the key aspects of all EMPIR projects is impact. How is the information that's being generated going to be used and disseminated. Well, for knowledge transfer, we've been able to disseminate work through the End User Advisory Group. We have a project website. There have been a number of conference papers and peer-reviewed publications. A case study will be made available, and there are some good practice guides that will talk about the best way to conduct these, experimental work. Another important aspect is to contribute to standards, and there has been a report submitted to the ISO TC28 working group, which is drafting a standard on multi-phase flow measurement. Another aspect is training, and this is being done through forthcoming workshops, webinars such as this, and also incorporation into academic work through the use of PhD students and researchers. For uptake and exploitation, well, there is the reference network of laboratories with NEL, DNV, and NORSE, and there have also been advancement in the tomography techniques due to the availability of real-world data to look at and analyze. We do have workshops coming up in the near future. These were to be held in a specific location, but obviously due to the coronavirus, that's no longer possible. So these will be split into 2 online workshops. The first of which will be on Thursday, the 4th of June, which will essentially look at work packages 1, 2, and 4. So the specification of the transfer package, more about the test program, best practice for intercomparison and measurement uncertainties, and describing the project outputs. These will be presented by NEL and the University of Glasgow. There'll be a second workshop, which will be towards the end of June. Date will soon be finalised, looking at primarily work package 3, the flow visualization methods, guidance on best practice for flow visualization, and describing the findings from the experimental test programs, both full scale and small scale, and the CFD analysis. And the presentations will include input from the remaining participants. Details will be available, I believe, after the end of the webinar. Oops, wrong way. And I'd of course like to thank EMPIR for supporting this program. If you would like to have further details, then please visit the MultiFlowMet 2 website and just search for MultiFlowMet on the internet and register for the workshops. Right, that's me.
Okay, thank you very much for that, Sarah. I think we've got a few questions that have come in. I think we may just have time for one question there, Sarah. Is there one there you may want to pick up, and then we'll just wrap up the event?
Okay. One question I've got is, what would a reference measurement network look like, and how long do you think it will take to establish? Well, there are already reference measurement networks available for single-phase flow facilities, and we can't see any technical or political barriers to forming one for multi-phase flow to look at interlaboratory collaboration and best practices and dissemination. Specifically, it would provide a framework to aid in a common approach to calculate multi-phase flow facility measurement uncertainty. Also to look at facility traceability and allow factory acceptance test procedures, increased level of intercomparisons, and in general just to provide confidence to end users that the verification of a multi-phase flow meter that's performed in one laboratory would be equivalent to that in a second laboratory within the uncertainties of the device and the laboratories. As for how long it will take to establish, it's probably going to take several years to establish fully, and it would hopefully involve a large number of multi-phase flow facilities, and we'd like to include NEL's new advanced multi-phase facility within that.